Hi there, in this video we're going to continue our discussion of implicit differentiation, so we'll continue with two more examples. This is part 3 of that video series. So our example here, find an equation of the line tangent to the graph of the cardioid x squared plus y squared equals that other quantity squared at the point 0, 1/2. And so notice here, this is a great example of, we have a curve. So now notice that I'm not calling them functions because they're not necessarily functions. We just have a curve and we would like to find an equation of the line tangent to it at a point. A cardioid, you will see this again in Calc 2 when you do polar coordinates. You may have already experienced polar coordinates in your pre-calculus course, but you will review them again when you get to Calc 2. Usually when I teach Calc 2, I make sure to review polar coordinates because it's been a while, right, since pre-calc that you've seen them. So this is what a cardioid looks like, and so this is our point 0, 1/2. So we want to find the equation of the line tangent to the cardioid at this particular point. So pretend that that's tangent. And so notice that this is a curve, right? No longer a function. To be a function, you have to pass the vertical line test. So this is definitely not a function, but we still want to be able to find these things, equations of tangent lines. And so I know then that to find the equation of the line, I need my point slope form. So y minus y1 equals mx minus x1, and we have the point is y minus 1/2 equals m, and then x minus 0. So it's just y minus 1/2 equals really mx. So we need to find the slope, and the slope is given by dy dx, or y prime, or other notation. Now here's our function, so let's find the derivative of y with respect to x. So I'm going to copy the function there, and to find the derivative, let's take the derivative of both sides. So I'm going to take the derivative with respect to x of both sides. And so I'm going to have, now I'm not going to do everything like I've done in the previous videos. I'm just going to take the derivative as I go. So the derivative with respect to x of x squared is 2x plus the derivative with respect to x of y squared. So that's going to be 2y times y prime. Y by the chain rule, right? So that was, the chain rule was applied there. Now remember, one of the things I said in the prior videos is that you can think of y squared as f of x squared. So how would you take the derivative of that, right? If you take the derivative of this with respect to x, you will have 2 f of x to the 1 times the derivative of f by the chain rule. So that's what this is. F of x is just a fancy name for y. And equals, now that do the derivative of this side, and this is looking a little messy, so let me get rid of my derivative there. And so I'm taking the derivative of this side, so I'm just going to write it out here with respect to x. And so notice that here I have to use the chain rule because I have quantity square, right? It's not just x squared. So I'm going to have my left side 2x plus 2y, y prime equals, now the derivative, the outside function here is the square. So I'm going to bring that to the front. So it's 2, the derivative of the inside left alone, to the 1, right? You decrease the power by 1 times the derivative of the inside with respect to x. So let me rewrite this. So I'll have 2, 3x squared plus 2y squared minus x over here times, now I take the derivative of this. The derivative with respect to x of something with an x, we just take the derivative normally. So that would be 6x. Plus, now here I have another y squared. So remember, y is implicitly a function of x. So that means we're going to use the chain rule there. So bring the 2 down, so that becomes a 4 times y to the first, and then by chain rule times the derivative of y. So times y prime minus the derivative of x with respect to x, which is 1. Oh boy. So now how do I solve for y prime? So this is one of the things in the previous video in part 2. I was saying that our goal is to solve for y prime, but notice here it's how do I even get them on the same side? So we're not going to necessarily solve for it as a function. What we're going to do is going to evaluate at our point, because then the x's and the y's will be numerical values and we can work with that. So instead of trying to solve for y prime as a function, we're just going to plug in our values and see what we get. So evaluate at when x is 0 and y is 1/2. So let's plug everything in. So I'm going to have 2 times 0 plus 2y times y prime. And our y is 1/2, and so on, right? So then we're going to go equals, then 2 times the quantity, and then plug in our zeros and our 1/2s here. So I'm going to have 3 times x is 0, so 0 squared, plus 2 times y is 1/2, so 1/2 squared, and then minus x. So x is 0, y is 1/2, x is 0, times, and then the same thing over here. Plug in the 0, so 6 times 0 plus 4 times y prime minus 1. So x is 0 and y is 1/2. So notice that this is going to make it a lot easier, right? 2 times 0, that's 0. 2 times 1/2, that's 1. So I'll have y prime equals 2 times that 0, that's 0. 2 times, that should be square. I think I was saying 1/2, so I wrote 1/2. So 1/2 square, right? I'm plugging it in over here. So 1/2 square is 1/4 times 2, so that's 1/2. So 0 plus 1/2 minus 0, that's just 1/2, times 6 times 0 is 0, so 4 divided by 2, so 4 times 1/2 is 2, so I have 2y prime minus 1. And so now let's simplify it some more. So I have 2 times 1/2, that's 1, times 2y prime minus 1. So notice how much easier this became after plugging everything in. So now I can say, okay, now I need to just solve for y prime. So bring this y prime over. So I'm going to have 1y prime minus 2y prime is negative 1y prime equals negative 1. So therefore y prime is positive 1. Divide both sides by a negative 1. So this is my slope. So I can say therefore the slope is 1. So going back to our equation, where was it? We had y minus 1/2 equals mx was the equation of our line. We can now finish the equation of the tangent line. So y minus y1 equals mx minus x1. I guess I'm just going to redo it. Y minus 1/2 equals m, which is 1 times x minus 0. So I just get y equals x plus 1/2 will be the equation of our tangent line. So going back to the graph, now that makes sense. So notice that this was the 0.01/2, and our y-intercept for the line, right? This is our line y equals x plus 1/2, as we just found, is that line. So hopefully this makes sense about when you're evaluating your derivative at a point and you have this crazy quantity like this. You don't have to solve for y prime as a function. So you can just plug in the point, your x value and your y value, and figure out what those numbers are. And notice how, of course, I had to be really meticulous and careful about plugging them in the correct places, not plugging them in the wrong places, plugging them in into the correct places and then simplifying appropriately. But then it became a much better problem than if we try to solve for y prime here in this highlighted areas. That would be really hard as a function, right? Because to get the y primes on the same side, I have to get this y prime out of this parentheses, which means you have a trinomial here times a trinomial here. So you have to FOIL that out, right? Use the distributive property very carefully to not leave out any terms. Likely there won't be any like terms, so it will be very extensive, but plugging in our values 0 and 1/2 makes it much better. All right, let's try our next example, which is finding second derivatives implicitly. All right, for our next example, find the second derivative of the curve x equals x e to the y plus 2 equals x minus y. So when you see something like this, it should be specified maybe with respect to x. So add that in there in your notes. Another way that you might see this is find, in using the notation, find d2y. So this means the second derivative of y with respect to x. So with respect to x, I'm going to abbreviate it like that, or you may also see it as find y double prime. But if you see this, somewhere in the problem it should say also with respect to x. So that's what I abbreviate with respect to x that way. So find a second derivative. In order to find a second derivative, we have to first find the first derivative. So let's take the first derivative. So meaning I'm going to take the first derivative of both sides with respect to x. So I'm going to have d dx of the left side, which is my x e to the y plus 2 equals, and then I'm going to also take the first derivative, the derivative with respect to x of the right side of x minus y. So here, notice that is x times e to the y. So there's an invisible times there, so that means we need the product rule. So I'm going to have the derivative of x times e to the y using the product rule says is the derivative of the first, so the derivative of x with respect to x, which is 1, times the second left alone plus the first left alone times the derivative of the second. The derivative of e to the y is e to the y by chain rule times the derivative of y, which is y prime. I hope I'm not sounding like a broken record, but think of y as y equals f of x, right? Y is implicitly a function of x, so it's like you have e to the f of x there. So if you had e to the f of x, how would you take the derivative of that? So that's what we're doing. That's why there is a chain rule here. Equals the derivative of the right side. So the derivative of x with respect to x is 1. The derivative of y with respect to x is y prime. Right? My y prime here is denoting dy dx, the derivative of y with respect to the variable x. And so now you can either solve for y prime here and then take the second derivative, or you can take the derivative and then solve for the y double prime. But I'm going to solve for y prime and then find the second derivative. So solving for y prime means get them on the same side. So these, I want them to be on the same side. So what I'm going to do is I'm going to add the y prime from the right, add it to the left. So here I'm going to have e to the y plus x, e to the y prime plus y prime. So I'm adding this one equals 1. And now everything that doesn't have a y prime, send it to the other side. So we're going to subtract e to the y. So I'll have x e to the y prime plus y prime equals 1 minus e to the y. And now you can factor out the y prime from here. You have two terms, right? The plus is what gives us the separation of terms. So I have two terms. When I take out a common factor, I should still have two terms inside. Equals 1 minus e to the y, divide by x e to the y plus 1. So divide both sides by this quantity. So I'll have 1 minus e to the y over x e to the y plus 1. And so now I find the second derivative. So take the derivative again. So when I take the derivative again, I'm going to get on the left side y double prime. Or with the other notation, this will be d2y over dx square. And so I'm going to get y double prime equals, now here I have to take the derivative with respect to x again of this quotient, which means then that we have to use what? Right, we have to use the quotient rule. And notice that there is a built-in product rule there. So this problem is all kinds of fun. So y double prime is now the derivative using the quotient rule is low d high, so the bottom times the derivative of the top, so times the derivative with respect to x of 1 minus e to the y, and then quotient rule, so minus, so low d high minus high d low, so 1 minus e to the y the top times the derivative of the bottom all over the bottom square. And then simplify. Now notice that this x times e to the y, we already took the derivative of that. That was what was originally here, x e to the y. This was plus 2, we have plus 1, but we already took the derivative of that, so you can just copy that over here when we take the derivative, or we can just go through and take the derivative all over again. So let's see, we have x e to the y plus 1 times the derivative of this. So the derivative of 1 is 0. The derivative of negative e to the y will be minus e to the y, right? That's e to the f of x. So e to the y times the derivative of y. So times y prime minus 1 minus e to the y. And then times, here we need the product rule. So product rule is that the derivative of the first times the second left alone plus the first times the derivative of the second, and then the derivative of plus 1 is just 0 all over the bottom square. Now, is there anything we can take out to simplify? These are being multiplied. I don't really see anything that we can take out, so we can just leave it. So it'll be x e to the y plus 1 times negative, let me rewrite that a little bit differently. That's just one term over here. So we can bring that to the front. So negative e to the y prime times x e to the y plus 1 minus, and we have a binomial there. So 1 minus e to the y times e to the y plus x e to the y prime. I suppose you can take out an e to the y out of here, out of the whole thing, and maybe be able to simplify some more. Can you see a better way of simplifying? So what I'm noticing, and hopefully you caught that as I said it, there's an e to the y here that's being multiplied, and there's an e to the y and e to the y here that I can take out. So when I take this one out, then I'm going to be able to take it out of the whole thing. So let me rewrite it. So it's e to the y prime times x e to the y plus 1 minus, so what I'm doing is I'm going to take this e to the y out, and I'll be left with 1 plus x y prime. Right, if we take the common factor of e to the y out, that looks like a 4, that's a y. So I'm going to have, write it at the front, e to the y times 1 minus e to the y, this term, and then times now the one that is left when we take out the e to the y. So 1 plus x y prime. I don't know that that helps us much. Sometimes it's like, how far do you simplify? Do you ever wonder that? Like, how far am I supposed to go, professor? Yeah, how far do you go? Until you can't, I guess, see anything else that we can factor out. And so here now I have the e to the y and e to the y, actually a negative, so I could take the negative e to the y out. But again, I don't know that it really helps us that much in taking it out, because I'm going to have, I'll be left with y prime x e to the y plus 1. I took out the negative, so plus 1 minus e to the y, and then 1 plus x y prime. Yeah, so I don't know that it helps us too much. Oftentimes we want to figure out where the function has horizontal tangent lines, and so we want to be able to simplify completely so we can set the numerator equal to 0, right? Because we have horizontal tangent lines when the derivative is 0. So when you have a fraction is 0 when the numerator is 0. And so that will be when we want to make sure that this is fully simplified if I'm trying to solve for x. But here, there's really not much we can do. So this is our second derivative. So now if I wanted to evaluate, so I'd say I wanted to find the acceleration at a point, I will have to also know, I will have to have the full point, and then go to the first derivative, plug that point in there to find what y prime is. And then for the second derivative here, I will have to plug in my x value, my y value, and my y prime value in order to find the value of that second derivative. Phew. All right, that's that problem. And I know what you're thinking, like, how far do I simplify? This one, I was honestly just trying to see, like, oh, if I factored in this e to the y, will I then get things that are like terms or that I can simplify further? But I don't think that there's anything really there to do. So you could just leave it as this crazy mess over here before taking out the e to the y. So if you left it at here, this will be fine. Like if I asked you for something like this, or a quiz or a test, which I wouldn't ask you this on a test because that will just take the whole time. But it's just in order to practice finding the second derivative of things. So on a quiz, I may give you lots of time to be able to do a problem like this, but then I would just leave you could just leave the answer like that. If you were asked to find though, like, where does this equal 0, then you want to make sure that you simplify completely. And if I wanted to write it in terms of just x's and y's, now I have to take my y prime from here, this quantity, and substitute it in there. And that will not be pretty for my y prime. So we can just leave it like this. Contact me if you have any questions or need any clarifications.